In the last video, we said that there is a level of savings that maximizes consumption per worker. And so what we want to do now is to actually put in an actual production function as an example and see how it behaves. And we're going to use a fairly common production function, although a simplified version of it, in order to see how capital evolves over time, how it's related to the savings rate, how a change in the savings rate affects growth, and how and what the sort of maximum level of consumption per worker is. So we're going to use what's called a Cobb-Douglas production function. And the Cobb-Douglas production function is any production function where capital and labor both have exponents less than 1, but that add up to 1. And so they have constant returns to scale. In this case, they're both 1/2, right? And so k to the 1/2 n to the 1/2 is the same as the square root of k times the square root of n. And so this has constant returns to scale. If you double both inputs, you will double the output, but it has decreasing returns to scale in both inputs, so both capital and labor. Now, what we want to do is divide through by n so that we have the output per worker and capital per worker that we had in equation 11.3. And then basically what we have is that output is just equal to kt over n to the 1/2, or the square root of kt over n. And so our change in the capital stock, kt plus 1 over n minus kt over n, that's the change, how much capital changes, is equal to s times the production function, kt over n, minus delta times kt over n. So this describes the evolution of capital over time, and the steady state will be when this left-hand side is equal to 0. So if we set that left-hand side equal to 0, right, then all we get is we move our delta over to the left-hand side, we square both sides, and then in order to get rid of the square root, and then that gives us our golden rule steady state level of capital, not the golden rule, just the steady state level of capital per worker, which is equal to s over delta squared. So you can see it's increasing in s, it's decreasing in delta as we would expect, and it's squared just because of the assumption we made about the production function. And so then we can find the output per worker, right? So this is actually, it comes out nice and easy, which is why we use it as an example, right? The math is nice and easy. Output per worker is just the square root of capital per worker. Capital per worker is s over delta squared. The square root of s over delta squared is just s over delta. So output per worker is increasing in the savings rate and decreasing in the delta and depreciation. So in the long run, output per worker will double when the savings rate doubles. That's probably not completely realistic, but it's fine for now, right? Basically, we want to make sure that output per worker goes up when the savings rate goes up. So we can actually graph this for this production function. We can show an increase in output per worker for any given level of depreciation when savings increases from 10% to 20%. So a couple things to note. One is that we see it's doubling, right? We're starting at 1, we're getting up to 2. So we doubled the savings rate, we double output per worker. And also that it's taking a long time, right? So we said, oh, well, long run growth doesn't depend on the savings rate, but this is actually taking a really long time to get us up to the new level of output per worker, right? It's taking over 50 years here. So an increase in the savings rate can lead to a fairly long temporary increase in growth. And if we look at the growth rates, what we'll see is that the growth rates in the beginning will actually be much higher than the growth rates in the later years, right? And so, if we have an increase in the savings rate, we would expect, much faster growth in, say, the first 5 to 10 years, and then slower increase in growth in later years. And so I think, that's probably what we saw after things like World War II, after natural disasters, is we see this boost in capital per worker and therefore output per worker in the short run, in that sort of 5 to 10 year time frame, and then a decreasing effect over time. So what about consumption per worker, right? We said, all right, well, we really care about steady state consumption per worker, not output per worker. And so in order to think about that in the steady state, we take output minus savings, but we know that savings is equal to depreciation in the steady state. So we can put in delta times K over N, that's depreciation, which will also be equal to savings. And then we know our equation for the steady state output per worker and the steady state capital per worker, right? Output per worker is just S over delta, and capital per worker is S over delta squared. So here we have S over delta minus delta, that's from this delta here for the depreciation, times S over delta squared, that's just S squared over delta squared. So one of the deltas cancels out. We have delta in the denominator of both of those fractions. So then it's S minus S squared over delta. And we can factor out an S and say S times 1 minus S over delta. And so now we can see the steady state values of capital per worker, output per worker, and consumption per worker, which is what we really care about for different savings rate for a given level of delta. So in this case, they put delta is equal to 10%. And what we see is that obviously when the savings rate is 0, capital per worker is 0, output per worker is 0, and consumption per worker is 0. And then as it increases, as the savings rate increases, capital per worker increases, output per worker increases, and consumption per worker increases up to 0.5. And it happens to be 0.5. If you took the derivative and set it equal to 0, you would see it's 0.5. But it's, symmetrical, right? The S and the 1 minus S, so it kind of makes sense. And you can just plug the numbers in and see for yourself. And so while capital per worker keeps going up and output per worker keeps going up, and they obviously reach a maximum at a savings rate of 1, consumption per worker starts going down once we pass our golden level of 0.5. Now, this is probably higher than in reality because we don't think our production function is, that exact production function. So we might want to have a more realistic production function before we solve for a more realistic golden level of savings. But this provides an example. And so finally, the question is, all right, well, anything that increases savings in an economy should increase capital per worker, increase output per worker, and anything that decreases savings should decrease capital per worker and decrease output per worker. And so the book focuses on Social Security. So Social Security is our retirement plan in the United States. It's a pay-as-you-go system. And a pay-as-you-go system means that the taxes, so we tax workers, right? So people who are working pay a payroll tax. There's both an employer side and an employee side of that tax. And then those tax revenues go to pay the benefits for current retirees. Rather than, like saving in a 401k or an IRA where you're actually saving, putting it into an account that you own and then taking it out when you retire. That would be like a fully funded system and could be run by the government, right? And so there was a debate about whether we should have a pay-as-you-go system or a fully funded system for Social Security. And we ended up with a pay-as-you-go system. And the argument here in the book is that that has led to a lower savings rate, which I think is definitely true. Therefore, lower capital accumulation and lower output per person. That would definitely be true in a closed economy, right? But we don't have a closed economy. And so I'm not sure how much you can argue that our capital per worker is significantly lower than it would have been with, a fully funded system or without Social Security. Maybe there's some careful econometrics that has made that argument, but I haven't seen it. So it's possible. But at the same time, the United States has very high levels of capital per worker compared to other countries. not that there are other countries that have similar levels of capital per worker, but we're not like lagging behind other countries. Although, of course, many other countries also have a pay-as-you-go retirement system. So maybe the argument is that, you know, all of these countries would have more savings, more capital, more output if they had either not had Social Security, which seems like a bad idea, or had a fully funded system, right? And so a fully funded system, the idea would be like you collect taxes, you put it into savings, public savings perhaps, right? But that could be invested in other areas, and that would actually increase capital per worker. So that's one possible argument there.